All right, let's jump straight into this explainer and explore the incredible bridge between chemistry and the electrical power that literally runs our modern lives. You know, electrochemistry can sometimes feel a bit like pure magic, but as we're going to see today, it's actually driven by some beautifully elegant logic.
Think about the device you're using to watch this right now. What's actually keeping it alive? I mean, its power doesn't just come from nowhere, right? It comes entirely from the unseen, microscopic engine of electrochemistry. Every single text you send, every video you stream, is made possible by this completely silent, invisible dance of atoms and electrons happening right there in the palm of your hand. It's pretty wild to think about.
We've got a lot of fascinating ground to cover, so here's our quick roadmap. We'll start with the power of electrochemistry, then look at redox as the core engine. Next, we'll step inside electrochemical cells, followed by calculating potential and conductance. Then we'll see how this plays out in real-world tech and corrosion, and finally wrap up with some key takeaways and tips.
Okay, let's kick things off with Section 1, the power of electrochemistry.
At its core, electrochemistry is basically a two-way street. Down one side of the street, you have spontaneous chemical reactions being harnessed to create electrical energy. Think of the battery in your TV remote. But then, down the other side of the street, electricity is used to force chemical changes that just wouldn't happen on their own. We call that electrolysis. So really, chemistry creates electricity, and electricity creates chemistry. The ultimate two-way street.
Moving right along to Section 2, redox, which is really the core engine of this whole thing.
You see, this entire discipline is built on pairs, and the absolute superstar here is the reduction-oxidation reaction, or as it's commonly known, redox. This is the absolute core of the science. In a redox reaction, one element loses electrons, which we call oxidation. Meanwhile, another element swoops in and gains those exact same electrons, which we call reduction. You simply cannot have one without the other. It is a perfectly balanced one-for-one exchange.
Now, if there is one thing you lock into your memory today, let it be this classic shortcut: oil rig. Oxidation is loss, reduction is gain. Seriously, write that down. If you keep oil rig in mind, you will literally never mix up these two foundational processes on a test.
All right, Section 3, inside electrochemical cells.
Remember that two-way street we talked about earlier? Well, this is where we actually build the roads. We categorize these physical systems into two distinct setups. First, we have galvanic or voltaic cells. Think of these as your power generators. They rely on spontaneous reactions to magically convert chemical energy into electrical energy. On the flip side, we have electrolytic cells. These are your power consumers. They absolutely require an external power supply to force those non-spontaneous chemical changes to actually happen.
Let's zoom in on a classic galvanic setup called the Daniell cell. If we treat it like a mechanical engine, we can see a really clear chronological process unfolding. First, fuel burns at the anode. In this case, it's a zinc electrode experiencing oxidation, meaning it's losing electrons. Second, those freed up electrons flow through a physical wire, creating our external circuit and providing electrical current. Finally, those traveling electrons arrive at the cathode, the copper electrode, where reduction occurs. Oh, and quietly sitting between them is the salt bridge, working hard to maintain electrical neutrality so the whole system doesn't just suddenly stall out.
Which brings us to Section 4, calculating potential and conductance. Let's look at the dashboard metrics.
So, to measure anything accurately, we need a baseline, starting line, right? In electrochemistry, that baseline is exactly 0 volts. This is the established potential of the standard hydrogen electrode, or SHE. But here's the thing, it only sits at 0 under super-specific standard conditions, a 1 molar concentration, 1 atmosphere of pressure, and a perfect 25 degrees Celsius. It serves as this dramatic 0 point from which all other chemical voltages are measured.
But obviously, real life is messy. It rarely happens in a perfectly climate-controlled lab at exactly 25 degrees Celsius with a 1 molar concentration. Which naturally begs the question, how do we calculate power in the chaotic real world?
Well, that's exactly where the math swoops in to save the day. The Nernst Equation is literally your best friend for calculating non-standard electrode potential. It takes that standard 0-point potential we just talked about and adjusts it based on the number of electrons and the specific reaction conditions. Plus, when you calculate the electromotive force, or EMF, by subtracting the anode's potential from the cathodes, you uncover something huge. If your total EMF is greater than 0, boom, your reaction is spontaneous. It'll run all by itself. But if it's less than 0, well, you're going to need to plug it into the wall.
Now, how well your cell actually conducts this electricity comes down to the liquid inside it, known as the electrolyte. Think of conductance like traffic. Strong electrolytes, like hydrochloric acid, completely ionize. They break apart entirely, basically opening up an 8-lane freeway for electrical charge to zoom through. Weak electrolytes, like acetic acid, only partially ionize, which creates a bit of a traffic jam. And according to Corrosian's law, at infinite dilution, each of these individual ions contributes independently to the overall conductance of the solution.
Let's zoom back out for Section 5, Real-World Tech and Corrosion. You know, electrochemistry is really the unsung hero of modern industry. It gives us those disposable dry cells for our flashlights and the rechargeable secondary batteries in our cars. It's even the magic behind hydrogen fuel cells. On a massive industrial scale, Faraday's laws of electrolysis dictate the exact electrical charge required to extract metals like aluminum. And get this, before this specific electrochemical process was invented, aluminum was actually considered more valuable than gold. Crazy, right?
But it's not all shiny gadgets and helpful batteries. Electrochemistry definitely has a dark side. It is the exact same process that slowly eats away at our bridges and vehicles through corrosion. Globally, rusting metal costs the economy over $2 trillion every single year. Because the environment itself essentially acts as a giant destructive electrochemical cell, we are constantly forced to rely on protective paint, galvanization, and tough alloys just to fight back.
All right, let's wrap things up with Section 6, Key Takeaways and Tips, especially for those of you studying for an exam.
Here is the absolute core math of the topic, all in one handy place. You've got your electromotive force, your Nernst equation for those non-standard conditions, and your conductivity formula. I highly recommend pausing the explainer right now and grabbing a quick screenshot of this table. Trust me, you'll be using these 3 formulas constantly.
But honestly, beyond just plugging numbers into formulas, your success really comes down to conceptual clarity. Remember that a spontaneous galvanic cell relies on oxidation at the anode and reduction at the cathode. Practice identifying which is which until it's second nature. But most importantly, try to master the actual physical flow of electrons. Truly understanding why an electron desperately wants to move from zinc to copper is vastly superior to just blindly memorizing a textbook. So, as we look toward a future absolutely dominated by renewable energy grids, advanced medical implants, and electric vehicles, one thing is incredibly clear. Electrochemistry isn't just dry history, it is literally the blueprint for tomorrow. Understanding this exact science is the very first step to inventing whatever comes next. So what barrier are you going to break with these equations? Keep exploring, keep questioning, and we'll see you in the next explainer.